Hi, so I hope you just had a lovely discussion about whether about Sherlock Holmes video, whether Sherlock Holmes used inductive or deductive reasoning. I would make an argument that he used deductive reasoning for most of his conclusions. I've got three examples of facts that he used up here at the top of your paper. Um, he used the fact that if you're in the sun, you're going to get a tan. That engaged women wear rings on their left ring finger, and that a governess does not make much money back in that day and time, are three facts that he knew and was able to use to deduce that the woman had borrowed the necklace because she didn't have the money to afford it herself, that she used to be engaged because she had that tan line on her finger, and that she had obviously been somewhere where she had been in the sun if she was even going to get a tan. So I would hate that I missed your discussion, but I would argue that he used deductive reasoning. All right, so talking a little bit further about inductive reasoning specifically, I know you know from your video last night that inductive reasoning is based on a pattern. And you can use inductive reasoning to tell the next terms in a sequence in math class. We use the word conjecture a whole lot in geometry, and it's basically a fancy way of saying an educated guess. So we know some inductive reasoning might be allergy to food. You know, you eat a strawberry and you have an itchy rash, we'll say. And then 2 weeks later, you eat strawberries again and again break out in an itchy rash. And you're observing a pattern that every time you eat strawberries, you get an itchy rash. So that's a great example of food allergy, of inductive reasoning, because you have that pattern there. Here is a mathematical example of a pattern. You've got Rodney is rolling marbles down a ramp. Every second that passes, he measures how far the marble travels. He records the information in the table below. So we've got second 1, then moving on to second 2, 3, and fourth second. It looks like in the first second it had already gone 20 centimeters, then 60 centimeters by the second second. By the third second it had gone 100, and by the fourth 140. So we can see that there is a pattern here that we're going up by 40 seconds each time. I'm sorry, not 40 seconds, 40 centimeters each time. So we would assume by the fifth second we'd be at 180, and by the sixth second we'd be at 220 centimeters. All right, I have another pattern here. I want you to, this is a really famous pattern called Pascal's triangle. So here's the triangle array of numbers. And so in your groups, I want you to read our history note here and see what patterns you can come up with. And then we'll come back on the other side and see if you found all of them. All right, so pause the video and see how many patterns you can find. Okay, so perhaps you noted that they're all ones going down the two diagonals on the outside. Perhaps you noted that it's 1, 2, 3, 4, 1, 2, 3, 4. Perhaps you noted that the two terms above add up to be the term in the middle. So 1 plus 2 is 3, 1 plus 3 is 4, 3 plus 3 is 6, so on and so forth. Perhaps, let's see what else we note. Those are the big ones. So what would you conjecture the next line to be? Well, of course, it's going to start with a 1. And then 1 and 4 is 5. 4 plus 6 is 10. This would also be 10. And 4 plus 1 is 5 again. Find the sum of each horizontal row. So that's obviously 1. This is 1 plus 1 is 2. This is 4. 3 plus 3 plus 1 plus 1 is 8. This is 16. Interesting. Then it looks like we're at 32. Do we see a pattern with the sum of each row? Hopefully you're noticing that each time we're just multiplying by 2, or some would say that this is 2 to the 0, 2 to the first power, 2 to the second, 2 to the third, 2 to the fourth, and 2 to the fifth power, so on and so forth. What would you conjecture to be the sum of the 6th row? We would guess that to be 2 to the 6th power, which would be 64. So how did you do? Did you find all the patterns? I hope you did. All right, so now we're going to read some statements and make some conjectures, some educated guesses. And so here we go. The product, so we multiply 2 even numbers. If we multiply 2 even numbers, does the answer always come out to be even? 2 times 2 is 4. 8 times 6 is 48. 10 times anything, right? It's going to be 10 times 6 is 60. So that appears to be true. The product is even, would be our guess. The relationship if A times B is -1. Well, let's think about what kinds of things multiply to be -1. 1 times -1 is -1. We also know that reciprocals, like 1/5 and 5/1, those would always multiply to be -1. So, because like 2/3 times -3/2, that's going to come out to be -1. So A and B are opposite signs. And they're reciprocals of each other. Okay, you try the relationship between NP and PQ. If point P is the midpoint of NQ, what could we conclude? Take a second, pause the video, and you try, and then we'll come back and see how you did. So hopefully you paused the video. If P is exactly in the middle, there's a couple of things we could conclude. We could conclude that NP and Q are collinear. If it's going to be the midpoint, you can also conclude, which I think is what they were wanting us to say, that, wrong one, NP has to be the same length as PQ. All right, then the last piece here is not all of our educated guesses are going to be right all the time. Turns out not all conjectures are true. You can prove that a conjecture is false by finding just one counterexample, one example to which a conjecture is an example for which the conjecture is false. And if you can come up with one time that it doesn't work, then it's false. The whole thing is not true, ever. Well, I mean, yes, we just consider it false. All right, so determine whether each conjecture is true or false. Give the counterexample for any false conjectures. So ABC and CBD form a linear pair. All right, so let me draw this. A to the B to the C and C to the B to the D form a linear pair, then the two angles are congruent. Well, no, like this could be 110 and this could be 70. If they form a linear pair, we know they have to add up to 180, but they don't necessarily have to be the same exact size. So my counterexample for this one is actually a drawing. I'm not going to even write that out in words. My drawing is sufficient. And we'll write down that that was false. All right, you try. If AB, BC, and AC are all congruent, then A, B, and C are collinear. So pause the video, see if you can come up with an example where AB, BC, and AC are all congruent, but A, B, and C are not collinear. Just one example for which that's false. Hopefully you pause the video. And this is a tricky one. Usually lots of my friends don't come up with this, but they can all be congruent and make a triangle. They don't have to be collinear. In fact, I don't know how they would necessarily be collinear if they were all congruent. All right, so your assignment now, take a minute and work these problems in the book, and hopefully I'll see you soon. All right, bye.